Why are you so slow? Okay. It's recording, I think. So, okay. So, um, let me add a couple things. So, one thing that is very useful to you, so far you've been measuring things, and you bring up the measurement box, which is kind of nice, and it gives you some measurements. Those aren't the only measurements you can take. You can actually do something called set measurements. If you come down here and analyze, and then at the bottom of the first thing, you have set measurements, and we can click that right there. And this gives you the list of different measurements, and actually, by default, what you're going to do is you're going to have this. This is what's actually selected there. You have some default measurements like length of your selection, a few other things. But then you have some measurements that are by default selected. You have area, you have min and max gray values, and then we have the mean gray value. And you probably have seen that as you pull up the measurements box, is that we have these different measurements that just kind of come up. However, those aren't the only ones that you can pull. There's actually this entire list of other cool things that you can know about your selected objects, which is kind of nice. And one of them being, if you come down here, that is really nice, is centroid and center of mass. Both these, what these are going to do is give you the XY coordinates of the center of the objects that you have selected. Now, the center being calculated in two different ways. The centroid being geometrically what maximizes the distance from all the edges. That's the centroid. And then the center of mass, this is essentially going to be the same thing in a binary picture, but if you have something else, you have different intensities of what you select is going to weight the pixels by their intensity, and then essentially use those in the same way that something with mass would have mass, and so things with higher intensities have higher mass. Or you can flip it and go the other way if you want to invert it, and then it will calculate a center that is weighted towards more intense pixels. So there is that as well. So all these are kind of the same. So I'm just going for this point, click centroid. Okay, so this is going to give us the XY coordinates of those points, which is kind of useful. So for instance, let's do this. Let's go, and I'm going to open up an already segmented thing from lab yesterday. You have here. I'm going to go into committee. No, not committees. What? Classes. You want to see what I have for curriculum committee? Not really, because I think I have an already segmented. Okay, here we go. Okay. Do you guys recognize what this is? This is the red tiles that I've segmented already. They're wonderful and happy. Zoom into one of these here real fast. And I'm going to, I just want to get the approximate area of this. So you go control measure. Okay. And what we got here is area of 418. So that's going to help me select these. No, I don't want to save that measurement. Unselect that. Zoom way back out. Not that far out. There we go. My image J back here. And let's say it's 418. So let's go from, say, 200 to 600. Any circularity. Display results. Summarize. I want to show the outlines. Just make sure I'm selecting things well. Okay. Okay. So if we look here, okay, so we've selected things. It looks like well, you can't see anything up there. So just imagine here with me that everything's been selected appropriately, because that's what it looks like to me. That's nice. And if we go, again, we have our count, which, by the way, this count is different than yesterday because I selected more further down. I wanted more points. So you're not looking at me like, you got a different number. Yeah, I got a different number. It's Friday. I'm talking in weird voices. Excuse me. Our results window looks like. This is what you had before, where it count up the numbers. You'd have the areas again. You have the mean, min and max, which in this case is absolutely worthless because they're all going to be 255, whatever. But here's the other thing that you get. You have your x and a y. This is the x and y coordinates of the centroid. the center of each of these points. This is kind of nice. We can actually get, and this is going to be important moving into next week because we're going to begin spatial analysis. I've included image analysis kind of in this umbrella of spatial analysis because in some really real sense, images are spatial data. It's not just a lump of intensities that we can analyze, but their intensities, we have the values of these pixels, but then they have some sort of spatial relationship to each other. They're not just random. At least, ideally, they're not random. That's how you make a picture. Okay, and what we can do with this is we can actually save this as an XLS file. So I can save the output of these measurements as an XLS file, which means I can export all these X, Y coordinates. Actually, I'm going to do something here. I'm going to get out of this. Okay, so here's a funny thing with images. The origin on images, just crazily enough, is in the upper right-hand corner. So it goes from 0 to whatever pixel y is here, and it goes 0 to whatever y is here, which is not typically what we think in graphing. So normally we think of the origin being in the lower left, where you go and that way. So one nice thing, if you're going to get x and y coordinates and you don't want to be like wrong, get rid of this. You want to select. You go to analyze, set measurements, and then there's one down here, invert xy or invert y coordinates. What this will do is set the origin down to the lower left-hand corner so it matches what you would intuitively think of being a graph. So if you're going to use these in some sort of analysis and you want them to line up with what you think and not all be upside down, choose your centroid or your center of mass, whichever one you want to, and then down here, invert y coordinates as well. So we're going to invert y coordinates, hit OK, do my whole analyze thing again, analyze particles, everything should be still set, hit my cool little boxes, and then come back here, go File, Save As. We're going to save this in an XLS file. I'm just going to call it results.xls. Okay. Now, I'm just going to show you something because I don't know. You probably believe me, but I just want to now plot all those points in R so you really believe me. It makes sense to me in my head, so go with it. I'm going to open up R too. Okay, so XLS, actually there's no good way. So there is a package in R that will import XLSX files directly, but not XLS files. This kind of comes back to when I was talking about data sources before. XLSX is actually an XML file, pretty easy to parse. The old XLS files are like proprietary binaries, and they suck, and yeah. Maybe I shouldn't put this on the web now that I've told Microsoft that something they made is horrible. They'll find me, shut me down. I don't care, let them come after me. Okay. Well, they must agree with me because they changed it, right? Oh yeah, I'm good. Okay, all those results like we did before. I'm going to go File, Save As. I'm going to save this as a CSV so we can import results. CSV, save them. Yes, use the text CSV format. I was serious about that. I wasn't confused. Okay, so I'm going to call the tiles. I'm going to change it to the results. Read them in. And hey, look here. We got the area, mean, min, max, x, and y. And we can plot those. Do y tilde x. Plot them, please. Zoom it, please. And there we go. We have an approximation of what you had before. I made them in these nice squares so they should look like tiles for you. In case you'd be confused otherwise. If I made them circles, maybe you wouldn't know what they were. No, I believe you would understand. So that approximates now this that we see. This And that. So we got our points into R. And now if I wanted to do some cool spatial analysis, like what is the spatial distribution of points, I can do that, which we will talk about next week. So that is how to extract XY coordinates from particles that you find in these images. Okay. Now let's take that to the next step. Imagine you have all these particles, and now we have them in some sort of series of images, like a movie or something else like that. We want to get them out. And then we want to detect motion, because, hey, that's kind of the next logical step. After detecting individual particles, we want to go on to actually figure out how they're moving through space. So there's a couple ways to do this and a couple ways to set it up. The easiest way is, so you need to be somewhat intentional as you're going through and actually thinking about setting up an experiment like this. However, in all honesty, shut this down. If you're handy with ImageJ and some other image processing stuff and maybe some videos and get rates of things out of YouTube videos if you really want to, speeds and cool stuff like that. But if you don't want to make this too much work on yourself, you need to be a little bit intentional about how you're doing this. So first off, if you're setting up an experiment in which you want to detect motion or track motion through space, one of the things is you have to recognize is that you are again getting a two-dimensional image of a three-dimensional reality. So one of the things that could happen is something can move closer or further away from the camera, and that is going to be hard to detect with a single image. Now, there's ways that you can get around this. You can take two images and get like coordinates in both, 2 dimensions there, actually 3 dimensions. Each one's getting, one of them's going to repeat length or something like that. But you can get distance from the first camera as well from a second camera. However, the other way to get around that is to just try to limit movement in 2 dimensions. If you're having something in water, I don't know why I tried to say like all these words with A that were more complex. Anyways, if you have something in water, you could just make the water really shallow and try to limit something's movement. Now, you'll have to decide in the experiment whether or not that's useful or not, or whether that's going to bias how things are moving or give you some sort of unnatural circumstance, but there's things like that. The next thing that you have to decide is how are you going to capture your images? And there's a couple ways to do this. Number one, you could actually capture video itself and then extract images from video. There's a few different ways to do that. There's a handful of programs that you can get that'll actually burst video into individual images. So for instance, in ImageJ you can do it. You can come into here and then you can go into import, and there is a thing where you can import AVIs. And then you could actually get individual image sequences out of AVIs. That being said, having used this a lot, ImageJ is very finicky about the kinds of AVIs that it accepts. It only accepts uncompressed AVIs in certain containers. So the point here is that most of the AVIs that you try, it will say are unsupported. That's just the nature of ImageJ. So it's probably going to behoove you to use something else. I've only done this myself on Windows and Linux, and then there's also some things in Mac that I've really quickly looked up. So if you're in Windows, there's a program called VirtualDub. All one word. And this is something I've used before. It's free software. I believe it's also open source software, though I don't remember off the top of my head. And this will, very easily, you go into File, Export, and Export Image Sequence, and I'll take just about any video that it reads, and it'll export to an image sequence. What? Did you do this a harder way?
Yes.
I don't remember.
Last quarter.
How'd you do it? I thought we got...
No. This is a very bad process. It's terrible.
You
I don't
got...
remember what I did. It doesn't matter.
You guys were capturing time-lapse images. That's easier.
No, never mind. Continue.
Okay, wait. Oh, were you trying,
We had to convert all the videos to frame rates, but we didn't actually take nice video
okay, yeah, that's the other thing that you did. Okay. Also, well, this is the same thing. Okay, so also VLC will do it as well. And both of these, hypothetically, do this fairly automatically. However, Jenna has found that you can break them. And actually, you can break them both. They're both breakable, so it's probably the video's fault, not the program. Well, it's probably the program's fault because it doesn't handle videos. Anything that you can get VLC on, VLC will do it. On Unix, the best way to do this is a command line program called avconf or ffmpeg. Both of these will do it really nicely, and they handle basically just about anything. Unix or Linux or whatever. Probably only two of you in this class that care about that. And then on Mac, you can use VLC as well, and that's really the only thing I know on Mac that will do it. There's probably more things out there, but I don't use Mac, so. I think actually, technically, you can get all these Unix programs, AV Convert and FFmpeg, onto Mac as well, because it's a Unix-based system as well, but I've never tried it, so. So all these programs you can take and you can convert a video into a sequence of images or a sequence of frames from that video, and then we deal with them after that. Okay. The other way that's actually a little bit nicer and easier to work with is to use a camera to get time-lapse images. So it's just taking once every 5 seconds, or it's taking once every 20 seconds or something else like this. And so that's easily doable as well. It depends on the speed of the organism that you're trying to track. If it's going very fast, maybe you want to record video. If it's going more slowly, it's nicer just to collect time-lapse images. And so, and honestly, if you can get away with doing time-lapse images, do it. Just remember to keep in mind your sampling rate and how quickly the animal is moving again. So, all that being said, at some point here, you're going to have a sequence of images that show some sort of movement. And let me give you an example of something that looks like that. Okay, so Mo, I was going to grab some things from you, but I actually forgot to ask you.
You can do it.
But I forgot to ask you for the images.
We can use them for that.
Okay. I still don't have those images. These. Get rid of these results. Okay. So, how do we work with a bunch of images in ImageJ? And the answer is that we use a word called a stack, an image stack. And so to get an image stack into there, we go into File, Import, and then up to Image Sequence. And then you go ahead and go to where image sequence is located in here. And then you select any image in here. It does not matter what image you select. You can select like this one. And it's going to bring up a small dialog here. And what this does now is it gives you several options for actually importing these. Number one, the number of images and the starting image. So it orders the image, I think, by either name or by file creation date, time. And you can start the image with any image in the sequence. So like imagine the first 10 minutes or 10 images were images of junk. You can start with the 10th image or something else like this. And then you can select the number of images that you import. If you want them all, just go ahead and leave starting image at 1, number of images at 65 or whatever it is. And then also you can get an increment. Imagine that you sampled it to a high rate. Whatever. You can cut this down by increasing the increment to 2, which means that you'll only import every other image. We can scale the images as they come in. We can convert them to 8-bit grayscale automatically as they come in, although for most things I suggest not doing that right away. And then also, here's a really big one, is use virtual stack. So a virtual stack is very useful because we are loading up lots of images. If these are big images, this is going to use memory very quickly. And if you don't want to use up that much RAM, you can use a virtual stack, and instead it will not load all of the images simultaneously into RAM. It will load them up and dump them out as is needed for your viewing pleasure. So it won't load everything up at once. So that's kind of nice. So those are useful if you're using tons and tons. In this case, I don't need them because they're small images and I only have 65 of them. So we hit OK. I'm going to leave all the defaults. And it's going to take a few moments here as it loads them all up, and you get something like this. Down at the bottom, you have a slider here. Like advance. And actually, this is exactly, so what I'm telling you today is actually exactly what Ray Lee was doing when he was, I mean, this is what I first learned in his lab. Actually, part of it. The tracking part of it. He does this like an old school way where like he marks them all with a dot because he can't like, because it's really hard to track individual animals in that field that he has. So that's tougher. But in this case, I'm going to show you a way that you don't have to actually track them automatically. So let's talk about segmentation in an image stack. So here's a kind of an interesting thing that an image gives. If you haven't done this before, can you think of anything that you can leverage about all these images that would help you segment your thing of interest apart from all of the things that you're not interested in? Some of you have done this before, though, and that makes it too easy just to say it. Yeah, maybe let someone else think about it. Maybe in a moment. Can anyone who hasn't done this before think of some way that something that you could do? In theory, like what kind of aspect of this could we use maybe to segment?
Stuff that's the same image to image.
Yes. Very good. Yeah, so what we can do is we can use differences between images image, which is kind of nice. And so to do this in ImageJ, what's really nice is if we just had a picture of the whole background by itself without the animal in it, and then we could then subtract this image from an image of just the background, and then we would have just the animal, right? Unfortunately, I didn't get that. There's a way around that. We can simulate an image of the background with just no animal in it. And the way that we do that is to average all of these images together. And so, since this organism's moving around, it essentially takes away the organism. So none of these, you'll notice none of these, they all have this bright process. No, it's image. No, it's analyze. Wait, where is it? Hold on. Yeah, it's an image, and you go into stacks, and you go into Z project. What we can do is we can do functions on these images. We can find the max intensity and sum of them and get standard deviations, or we can get the average intensity for all of them all the way through. And if we do this, pop me out another thing. And here's another image. This is a single image, and you'll notice it is the exact same thing we had before, but there is no nudibranch in there anymore, magically. Like a magician, I have made it disappear. I feel very accomplished. Okay. And then what we can do to get the segmentation is that now, wherever we can take each of these images, and wherever these images differ from just the background image, we can highlight those. And the way that we do this is taking the difference between this and this. And again, we can do this with process, image calculator, and our image 1 we want to be the stack. So this stack, and it's named onThink. Image 2 we want to be the average picture. So you see this says average onThink there, which I am. I'm just an average onThink. And then the operation that we want is difference. So we can do all sorts of cool operations that compare these images. The one that we want here is difference. And it's nice to create a new window with each of these. We don't actually want to do it to one of our original ones, because if we want to redo it, it's nice to be able to just not go back to opening up the image sequence again, but just to go back to these open images here. And that works if it's a fairly small stack as well. If we have really big stacks and we have virtual stacks, sometimes you have to undo this and actually overwrite the original. But in this case, we can do this. So we do that. Yes, I want to process all. I get that, but. And what we come up with is this. So let's watch this. Okay, that's fine. So there it is. It's basically yes, I don't want to get all of that reflection-y stuff out of there. I just leave it. Here we go. Move it out. Move it out over here where I think it might be. Move out here. Move down this way where I think it might be. I don't know. Okay, so let's let him go for a little while. Yeah, I'm okay with this. Just do it. Okay, so you know. There. Oh, I do say so myself. So you see the actually, is this? Okay, now we have this. Hi, little buddy. He just moving. Okay. And then the next thing is like the other things. We're going to convert this to 8-bit. I'm going to threshold it, so color. Wait, no, adjust. Threshold. And here's the difference. When you do the threshold, you need to kind of like go through the entire stack and make sure that he shows. Whoa. That. What'd you do there, buddy? Boop. I'm kind of curious. What happened there? Okay, so. Oh, this is actually really nice and clean. That just makes me happy. Good job. Okay, I'm getting little. Okay, so there we go. So I'm gonna apply that. Okay, that looks pretty good. It's going to bring up this, okay, it's going to want to convert the stack to binary, and one thing it's going to ask you is calculate threshold for each image. This is going to appear like, yes, I want the threshold to be applied to every image. That's not what this means. This means, do you want to go back and reapply the threshold differently for every single image? And you don't. So, deselect that. Yeah, okay. And now the threshold should be applied the same for all the images. And this was actually a really easy one. Sometimes you really have to jigger with it for a while to get something good. And ooh, I do have some of your images, I think, and they need more jiggering. So maybe I can do that after this. But here's another thing: is that we also have like these random like little dots showing up. I mean, yeah, like that one. But I don't know if you can see. But there's a few other little specklies up here. But now that we have this, that's just. That looks so perfect. I love that. And I just like how this, when I first had this happen, when I first did this, it just made me happy how like you could get like this little black and white thing moving. And I don't know. That just this is happiness to me to see like I made like this little trace. Anyways, okay. Now the next part to this is to go into plugins, and there's several different plugins for actually tracking particles. It's essentially the same, similar to the particle analyzer, but does it somewhat differently. And we're going to come into tracking under plugins. So plugins, then tracking, and then mtrack2. Like you see, you actually have a host of different things to track with. Just like, by the way, with segmentation, you have a lot of cool ways to segment an image J. I would suggest if you actually use this, try out some of the different segmenting. I only really had time to go over threshold segmenting in here. There's a ton of different ways, and if you have to like mess with one, I would suggest this one. The simple interactive object extraction is kind of cool. You tell it what is foreground, you tell it what's background, and then it uses that information to try to extract things in color, and it's kind of really cool. And then you can save profiles with that segmenter and then apply them to a lot of other images. So that's a little side. If you have time to play with other ones, that's the next one I play with. It's a little bit more complicated, but it works really well, and it's really cool. Anyhow. But like that, we have a lot of things for different tracking. I'm just going to show you one of them, mtrack2. And in this, what we can do is, like before, we can set a pixel range for things that we want. So minimum object size in pixel to maximum object size in pixel. Our thing is pretty big, so let's actually set it up to like 20, which is not huge. 20 pixels, but our object is always well above 20 pixels. And the maximum velocity. What this is how many pixels are we allowed for an object to move between frames and still count it the same object? If I am really certain about what I'm doing here, like this, I only have one object in there, and I know it's moving somewhat, I try to set it pretty generously. So, for instance here, this is 444 pixels across and 187 above, so I would do something, honestly, in this case, like 200, because I know it's really the only object I'm tracking. If I have something where I have multiple things I'm tracking in there, I'd probably be a little bit more persnickety about the specifics of how far something can move and try to measure, okay, I'll try to find something that's moving really fast in this image that I want to track. I'll see how many pixels does it move between images and try to set that to my upper bound. Because if you don't, what will happen is you can just have things kind of appearing out of nowhere, and it will just say, oh, this thing is that thing now, and it's that thing now, and it'll just kind of, it won't really capture what you're trying to measure because it's not constraining between frames how far something can move. If it can move anywhere, then it could really, any point in the next image could be transferring to that pixel or to that object. In this case, I only have one major object in here. I'm not too concerned about it. And then also a minimum track length. This is nice and constrained because sometimes things just kind of show up and hang out there for a little while. And those aren't necessary things you want to track. So you can set this higher to make this essentially more selective as well. So I'm going to say minimum track length in frames of 5. Generally, I then select all of these. I want to save the results to file. I want to display the path links, so this will actually show how far things went. I will open up a new thing that shows the labels, show the positions, and show paths. That's kind of cool. You hit OK. It wants to save your track results, just as trackresults.txt. We'll open that up in a second, and I'll show you what's in there. Windows. You're going to open up some new windows. What? Oh, here they go. They're small. Okay, so here we go. We have like this one that shows you what is the actual path followed by this thing. The image. We have another stack that it makes that, yeah, let's just make this. That will go through, and it actually reads out now which object that is and where the thing is. Oh, I inverted Y, so it's actually reading at the opposite side. So, oops, that's why it doesn't line up. And oh wow, so it counts the poop as it. And it calls it number 2. It's perfect. Here we go. I couldn't have planned that any better. That's fortuitous. That makes me very happy on a Friday morning. That's great. Okay, and if we go back in here, we have that track results.txt. Open this up, and it's just going to be a tabular file. I think it's tab delimited, if I remember right. It's not a comma separated variable. Fine, take forever to load. Here we go. And what we have here in this tag delimited is that we have our frame, we have then X and Y, and this does this kind of weird because what it does is it gives you X and Y of object 1, and then in another column it gives you X and Y of object 2. That's not how I'd like it for like analysis in R, but it does, okay, we can work with it. So we have frame, X1, Y1, so here's the X and Y's of all of our points that animal went through there. And again, if we want to convert pixels to actual measurements, we could go back and actually set measurements or set the scale we've done before if we have something in there. And the other nice thing here is if you go down to the beginning or down to the end of each track, the length of the entire track, the distance traveled. Now, these might seem like the same. The length is the length of the whole track. The distance traveled is the distance between the beginning and the end of the track. And then the number of frames that's around for, and then also number 2, where did it go? And then you got, no, it stayed right there. It's only there for 5 frames. Okay. So that is the basics of doing that. I'm going to show you one more example real fast of this. And something that wasn't quite so clean. Are there any questions on this so far, by the way? all these. Take care of you. Sound just came out of my mouth. Okay, let's see, where did those go? Documents. Oh yeah, I was looking at them. We got goldfish. Oh no, that's not what I do. I want image. Okay, file. Image sequence. Yeah, keep all the defaults. Awesome. Okay, and you'll see we got a fish here. Woo! Now here's one thing: the frame rate on that will kind of mess things up. So let's work with this. So image stacks, Z project. We want averaging 10. So we've got the average. We're gonna go process, image calculator. The difference of that and the average goldfish. We do that. Yes, I do want thing here, and then what we have here is like that. Let's see where he moves. Jamming out a little bit there. Oh, that's way off. I suck. Crop. Process or image type 8-bit process. Now image adjust threshold. Okay, now let's look at thresholding this. This is a little bit wonkier because it moves all over the place and we got all this gunk in there moving around. So we have all these swirling little dotty things. So actually the best thing to do with this is to find the place that you least pick up your object, like here. And then try to adjust your threshold so you get that and nothing else. Okay, that's not helping. Okay, so actually I can't get rid of those little dots. Totally. Another. What's that? Yeah, and I can do that, yes. Problem is like that gets really small there, but yes, that's one strategy I can do, and that will be part of the strategy. So okay, so I got that. I'm going to apply that. But another thing that I can do is use this other thing called process binary and erode, and this will essentially make everything smaller, which will differentially, like, essentially erode away very small things into oblivion, and so they're just gone. So the noise is gone. Yep. And then I go ahead and do the same thing as I did before and track the image. So
if you look at the upper frame, there's a part where it catches the reflection, so when you're looking at your analysis, you would need to account for that.
what does it do back here?
It catches its reflection, but you can't crop it because the goldfish goes up there at some point.
Oh yeah, so yeah, it catches it right there. Yeah, but we took care of that mostly. So it's 1, 2, 3, 4. Yeah, it's only for 4 frames, so we could set the frame rate or the minimum track length up, and it would do that. The other thing that you'll notice is that it actually splits into 2 sometimes.